In this video, we're going to extend on the idea of expected value to define the mean, variance, and standard deviation of a random variable. So we've already seen that the long-term behavior of a random variable x is given by the expected value of x. We refer to this expected value as the mean of the distribution of x, or just the mean of x. And we're going to get fancy, and we're going to use the Greek letter mu to denote the mean. And if we're talking about two or more different distributions, we might use a subscript to do it like a mu sub x to make sure that we're talking about the mean of x in that case. All right, so let's consider two different distributions here. Let's suppose that x has equally likely outcomes, 3, 4, 5, 6, 7. Let's suppose y also has equally likely outcomes, but the outcomes are 1 through 9, 1, 3, 5, 7, 9. We can compute the expected values, just like we've done before. They're equally likely outcomes, so each one has a probability of 1/5 of occurring. So in this case, to do expected value of x, we would have 3 times a fifth, 4 times a fifth, and so on. We would get 5. Notice if you do the same thing for expected value of y, we do 1 times a fifth, 3 times a fifth, and so on. We would also get 5. So, like I mentioned before with the subscripts, the mean of x is 5, and the mean of y is 5. So notice that these distributions, we have the same mean and what looks like the same PMF, right? They were equally likely. However, it's clear that the two different distributions really are different, right? If we look at the numbers, the distribution for x is certainly more bunched around 5 than y is. We've got more spread in y than we do in x. So what we want is some sort of a measure that helps talk about the spread of a distribution. And so that's where the variance comes in. So the variance is defined as the expected value of the square of the difference between x and mu. Okay, so let's talk about this for just a second. X minus mu is a distance. It's how far x would be away from the mean, right? That would be the difference between those two things. Now, it's possible that those differences could be negative and it could be positive. We're doing expected value here, and it turns out that if I didn't have this squared here, and I just had x minus mu into the expected value, I would always get 0 every single time. We'll talk about that a little bit more in class, why that's true. But trust me for right now, if I didn't have this square here, if this were gone, and we just had x minus expected value of x minus mu, you would always get 0. Okay? So to make these differences all positive, we do the square here to help us with expected value. So by definition, that would be taking the x minus mu and squaring it, and then multiplying it by the PMF, and then summing it up over the entire support. All right, so let's do that for the two distributions above. We already found that the mean was 5. So we plug in each individual value for the x, which was 3, 4, 5, 6, 7. Subtract the mean from each of those. That's what this says to do. Square it, and then multiply by the PMF. If you go through that process, you'll get 2 here. If you do the exact same thing for y, now notice that we have different distances here, right? 1 minus 5 is -4. Squared will give me a 16 on that term, whereas up here it was just a 4, right? So we're weighting this more because it's farther away from the mean. And in that case, you'll get 8. So the variance of x is 2. The variance of y is 8. All right, so we calculated that directly from the definition of the variance, but sometimes there's an easier way to calculate the variance, and it's equivalent to this definition. So we're going to use those properties of the expected value that we've talked about in a previous video and talked about in class. So if I want to do expected value of x minus mu squared, let's FOIL out the inside. So we get x squared minus 2 mu times x plus mu squared. And now we can break up the expected value over those inside, right? Remember, expected value breaks up over the sums, and we can pull constants out. So mu is just a constant, so we can pull the minus 2 mu out in front of this one. So we get expected value of x squared minus 2 mu expected value of x, and then plus expected value of mu squared. Now, a couple of these we know the answers to. Expected value of x is what we call mu, so we can replace expected value of x with mu, and expected value of a constant, mu is a constant, we just get mu squared here. Now we can simplify this because this is minus 2 mu squared and then a plus of mu squared. So we get expected value of x squared and then minus mu squared. And then remember that mu is just expected value of x. So this gives us a little bit more of a, I will say, a straightforward way to calculate the variance of a random variable. And we're going to use this formula a lot. So this is one you'll definitely want to remember. Let's put it in action. Let's say we have a random variable with this PMF, 4 minus x over 6, where the only values of x are 1, 2, and 3. We can calculate the expected value. Remember, expected value is x times f of x. So x is 1, we put 1 in for x here. X is 2, we put in 2x for x here. 2 in for x here. X is 3, 3 here. Do the simplification, you get 5/3 for expected value of x. So that would be your mu. Let's now do expected value of x squared. Well, do the exact same computation except squaring each individual x. You'll get 10/3. Now if we use the formula we just came up with on the previous slide, the variance is expected value of x squared minus expected value of x quantity squared. Plug in our values and we get 5/9. One more thing that we'll be doing the computation of, which is actually very, very straightforward once you have the variance, is the standard deviation. The standard deviation is just the square root of the variance. Remember, the definition of variance was doing x minus mu squared. So in some sense, we're undoing the squaring after we do the expected value. It doesn't quite work, but that's the idea. And in some sense, what this gives us is how far, on average, each outcome is from the mean. So in this case, in the previous example, since our variance is 5/9, the standard deviation here will be square root of 5 over 3, if I were to simplify that. Decimal equivalent here is 0.745. I said in some sense, this is an average value of how far each outcome is from the mean. If you actually did 1 minus 5/3, 2 minus 5/3, and 3 minus 5/3, you should get the average of, well, that's 2/3 apart, that's 1/3 apart, and that's 2/3 apart. Oh, sorry, 4/3 apart. You should get an average that's about a little bit bigger than this 7.745, I believe. So it's not exactly the average, but it's close. And this, again, it gives you an idea. The whole reason why we're doing this is we're trying to figure out a measure for how spread out the data are. Okay, how spread out the distribution is, I probably should say. We're not actually dealing with data in these particular cases. That's more of a statistics topic, which we'll touch on a little bit, but you'll focus more on that next semester. But it really does give you an idea of how spread out things are. So the bigger this number is, bigger the variance or bigger the standard deviation, either one, tells you that the distribution is more spread. It gives you more variance. All right. We'll talk about more of this and some other concepts out of section 2.3 in class.